Constraint-Aware MPC-RL for stable non-prehensile payload transport on quadrupedal robots. A quadrupedal robot can traverse terrain that wheeled robots cannot, which makes it useful for transport tasks. One of these transport methods is non-prehensile transport, in which the payload is simply placed on the trunk, so that objects can be loaded and unloaded without a gripper. The payload, however, is held only by friction, so trunk acceleration and attitude changes during locomotion cause it to tip over, and a fallen payload cannot be recovered. This study therefore proposes a control framework that transports an unsecured payload while suppressing tipping, without any additional fixture. The framework separates planning from execution. The body MPC takes the locomotion command, the support polygon, and a nominal payload model, and generates a trunk reference that keeps the payload center of pressure inside the support region. The reinforcement learning policy then tracks this reference and outputs full-body joint commands. The support polygon changes at every contact transition, and the payload tips most easily when it narrows, so reacting after tipping begins is too late. The body MPC therefore plans the trunk trajectory in advance from future foot placements and support polygons, imposing the payload center of pressure condition as a constraint, together with friction cone and wrench balance conditions. The policy takes the MPC reference and observation history and outputs joint commands. But tracking the reference does not guarantee that the stability conditions hold, because the tracking reward alone can be earned while violating them. Constraint costs on contact consistency and the virtual payload center of pressure are therefore added, and the policy is trained by constrained reinforcement learning based on P3O. The trained policy was first evaluated in simulation. It tracks the commanded velocity while adjusting the trunk attitude during acceleration and deceleration, and the virtual payload center of pressure stays inside the safe support region. Three policies are compared on the real robot. The first is a standard reinforcement learning policy that follows only the velocity command with a trot gait, using neither the MPC reference nor any constraint cost. The second removes only the virtual payload center of pressure constraint. Its three-leg support static gait and MPC reference tracking are identical to the proposed policy. The third is the proposed method. Gait frequency and training setup are identical across all three. The experiments use two payloads with different center of mass heights over a 5-meter course, and each of the 6 conditions was repeated 10 times. Experiment 1 evaluates the baseline with the high center of mass payload. In all 10 trials, the payload tipped over. Experiment 2 removes only the virtual payload center of pressure constraint. Again, all 10 trials failed. Tracking the MPC reference alone, therefore, does not prevent tipping. Experiment 3 evaluates the proposed constraint-aware policy under the same condition. The proposed policy succeeded in 7 of 10 trials. It completes the course with the payload upright, adjusting the trunk attitude during acceleration and deceleration. Experiments 4 to 6 use the low center of mass payload, starting with the baseline. With the lower center of mass, even the baseline succeeds in 9 of 10 trials. Experiment 5 removes the constraint, again with the low payload. The policy without the constraint cost also succeeded 10 times. With a low center of mass, the payload does not tip easily, so the policies are indistinguishable. Experiment 6 is the proposed method with the low payload. The proposed method likewise succeeded 10 times. The difference between the policies thus appears only where the center of mass is high and payload stability is hard to maintain. With the high center of mass payload, both comparison policies failed, while the proposed method succeeded in 7 of 10 trials. This is because the MPC-derived constraint costs carry the planning stage stability conditions into full-body execution. Finally, the payload remains stable not only in forward and backward walking but also under turning commands. Thank you for watching.